Bruno Sanchez is a postdoctoral scientist at Duke University, but he will be moving to Marseille very soon. He is also the co-convener of the Supernova Working Group within the LSST Dark Energy Science Collaboration, and has just led an accepted publication on doing SN1A cosmology with LSST DC2 images that he will tell us about now.
Thank you. Thank you very much. Thanks again. I want to take the opportunity to thanks again the organizers. It's been a lovely week hearing a lot about the LSST science. Oh, yeah. Okay. So as Gautam said, I'm a postdoc at Duke, so I've been working a lot with the Duke Cosmology group, but also this work has been possible because of the Dark Energy Science collaboration. A lot of people there involved in what I'm going to show you now. So this talk is about using LSST simulations, the DC2 images. So there's a part that's going to be about difference imaging. So how do we discover things? And then there's a part that I'm going to go all the way through from pixels all the way to cosmology. Okay, so we have been hearing this week about transients with LSST. And in this talk, I'm going to focus about cosmology and Type Ia Supernovae. So Type Ia Supernovae cosmology is booming right now. And many speakers have already stated what's the current rate of the discovery of supernovae, and then how it's going to explode when LSST comes online. This figure is from Daniel Skolnick, is about the white paper, and it's showing different redshift ranges at which SN1A cosmology is going to, or SN1A transients are going to modify our understanding and improve our understanding. It could be whether our local H0 determinations, redshift at almost 0.01, then up to redshift of 0.1, we have peculiar velocities and F sigma 8 determinations, and then at mid-range redshifts, we have what's the distance determinations of SN1A is going to help us understand the shape of our universe. And beyond, we've here amazing talks about strongly lensed supernovae and time delay cosmography. And in a wide range of redshifts, LSST is going to be the major contributor of our discoveries and our data will come from here. The Dark Energy Science collaboration is aiming to, really use this data for cosmology. So here I'm showing you what could be the summary of the objectives of Dark Energy Science collaboration, or DESC, which is to measure the dark energy equation of state and its dependence with the universe redshift or H. There's two parameters, W0 and WA. And here I'm showing you the constraint contours of these two parameters in year one and after the 10-year survey. And this, I think, Maria showed us how independent is SN1A from all the other probes that DESC is also building. So DESC's effort is centered around pipelines for analyzing this. So we all have heard what LSST is. Certainly, there's a lot of things that are yet to be defined. Survey strategy, observations, and the cadence and all. But it's certain, we're all certain that it's going to be detecting a large number of transients per night. A relatively high number of them is going to be SN1A. And after the 10-year survey, we're going to have 100 times more SN1A that we currently have with current experiments. So this means that the statistical errors is going to be decreased by 10. So now we have to control the systematics. That's the real task for us. And there are photometric biases and selection biases. And I think this is where I conclude the introduction of the talk, is that the difference image analysis is the cornerstone of transient detection. So if that thing doesn't work, then we're in deep trouble. And all the science, all the amazing science that we have been hearing this week starts after the discovery of the object. And this comes with a simple image subtraction technique, relatively simple. So this is critical for cosmology and many other science cases. So what we have run is a test. We've tested the pipelines for discovery, and we did it with DESC DC2 image simulations. So briefly, DC2 is a pixel level simulation of whatever LSST, Vera Rubin LSST survey is going to measure. This includes several effects, all the effects of the detector, the telescope, the atmosphere, the astrophysical sources, all the way to the pixel, including also cadence. It's an outdated cadence, and we know this, but yeah, it's what was available at the moment. So this includes SN1A point sources, and the full area of DC2 is 300 square degree, and from Wi-Fi steep 1 square degree of DDF for 5 years of survey. So it's a significant amount of data, but it's not even a half or a 10% of what LSST is going to be observing. So here I'm showing you from the DC2 paper how the images look like, what's the tiling strategy. I don't have a lot of time to explain to you what are the nuances and differences in each plot, but yeah, here's a GRI coad of the images. So there are galaxies up to a certain redshift phenomenon. We have used a subset of this data set, 15 square degree. So if you paid attention to Maria's talk, DES is 27 square degree. They have deep fields and shallow fields, but in our case, we only used Wi-Fi steep. So this is for 5 years, 15 square degree, roughly half the data set. And we processed all the raw pixels of this DC2 simulation and used image abstraction to detect the transients in this area. So this is almost 2,000 pointings of LSST telescope, roughly 106,000 CCD images that we have processed, and we have detected the SN1As up to redshift of 1. This is almost 6,000 of them. So in this plot, I show you what's the tiling that we have, and just marking the found and lost SN1A. Yeah, you can find this in the paper. So the distribution of the population parameters of the SN1A in DC2 are what I'm showing you here in the table, and also in the plots on the right. In the table we have that it's a SOL2 model, a PRL 2018 extended model. The rate model is a deal day 2008. There's an intrinsic scatter term involved here. It's like 0.15 magnitudes. There are no host correlations included in DC2, and the stretch and color populations come from double Gaussian distributions. So I'm showing you here in the lower panel the distribution of the peak MJDs of the supernovae. Maybe you cannot see it from that distance, but there are 4 seasons here: year 2 to year 5. So we have used for the detection, and then you can see how the peak of the SN1As that we have in our sample sometimes fall in the seasons and sometimes no, they don't. So we have used what's called the DIA pipe. This is DESC's difference image analysis pipeline. We created, I'm going to be running very quickly on this. So we created templates, so deep coads in year 1, and then subtracted images in year 2 to year 5. We detected sources, we associated them spatially, and we created light curves of these objects using forced photometry techniques. After that, so we can build the light curves. So there's a huge data set of light curves built from DESC that we created. So, and after that, we can fit these light curves with SNIa. Additionally, we can analyze them using simulations. So recreate this data set with catalog level simulations, Monte Carlo simulations, and apply a full cosmology analysis to infer the cosmological parameters. So I'm showing you here the first step, the results of the first step, which is the template generation. I'm not going to be talking about all the numbers here. We just show for template and the DIA season. Can you see the pointer? Yes, you can. The 5 sigma magnitude depth for point sources, and mean and RMS, and also the PSF size for template and for DIA seasons. So we created templates for this. The properties are good, except for U-band, which is something that's going to be appearing later on in the talk. So this is a nice picture. Took me a lot of time to find 5 supernovae in a field that I can show in a slide, but they are real. So I'm showing you what will be the nightly taken image, the template in the middle, and then on the bottom, I'm showing the difference image. And I'm also in red circles showing the detections of the DIA pipeline. And I'm also adding circles on the Type Ia supernovae that are in the field. We know this with truth catalog information. And also the signal to noise ratio of these point sources. So maybe you can't see in the distance, but some of them have a signal to noise ratio of 0.6, like this one, or 5, and they are not detected. There's no red circle on top of it. And these are the yellow ones, they are missed ones. And then we have the white ones with a signal to noise ratio of 10, 9 over here, and then 15. So doing this for the entire set of epochs that we have, we can build what it's the efficiency curve of our DIA pipeline. So we do this, we can characterize exactly what the difference image analysis performance is. So the number that we interested on is the signal to noise ratio 1/2, which is when the efficiency falls to 50%, what is the signal to noise ratio? And we obtain a 5.8. So this is very useful for simulations. We can also do it in magnitude space. So when you do it in magnitude space, you need to split in filters. They have different depth. And this is what we get here, a value for the magnitude 1/2 efficiency. All right. We can also combine every epoch for every supernovae and using the redshift information, obtain an efficiency of detecting an event. So what we also can derive is a 50% efficiency redshift value or redshift cut, which is 0.7. Of course, this is higher is better for this kind of metrics. Additionally, we can measure the photometric flux performance for our force photometry pipeline. I'm showing you here what is the fractional bias as a function of the magnitude of the SNIa. And also, so the shaded region here has very low stats, 7 events, so they're all correlated, the points over here. But roughly, we can see that from magnitude 19 to all the way up to 23.5, roughly, we're unbiased on the fluxes. If we also construct the photometric flux poles, we can additionally check what are the uncertainties in our pipeline. So we weight the bias from the true flux and use the uncertainty and the denominator, and getting the distributions of this, we can see if the pools look okay or not. So what we would expect is a zero mean unit dispersion Gaussian. For U-band pass, for instance, we found that it's a little bit biased and is not exactly correct, the uncertainties. And we speculate or think that this is due to the templates which haven't been so good for U-band pass. Also, we can quantify what's the fraction of outliers, 5 sigma and 10 sigma outliers in the photometry. Yeah. Finally, there's another interesting thing that we can do with all these fluxes and values is that we can check what is the RMS in our flux pool distribution as a function of the surface brightness of the host galaxy. So in these plots of the right, I'm showing you what is the distribution of the surface brightness, local surface brightness of the host, and then what is the scatter in our pools. So you can see how the scatter is increasing when the galaxy host is very bright near the supernova. So this effect is observable even in DC2 simulations. So it's also that has been observed by DES survey. So what we quantified here is when the scatter becomes twice, it becomes 2. So this means that the uncertainties are at least half of what they should be. What about the subtraction? So we all know that the DIA difference image analysis has contamination artifacts. So when the subtraction doesn't actually work, we see these weird artifacts that are labeled as a source detection. So yeah, in the simulations, we also have a lot of artifacts. We can quantify what is the fraction of them. I'm not expecting you to read this table, but we have quantified also the density in the sky of artifacts. So again, U-band pass is slightly worse. And also we recent work in DESC from Xu Liu, it's a graduate student at Pittsburgh, has been showing lately that the flags that the pipeline is already calculated are very good at filtering this. So we expect that a simple machine learning implementation can at least get rid of the obvious ones. Okay, so far we've talked about the DIA, the pipeline and the performance of it in numerous metrics. So I'm comparing here in this table the DC2 determination and the DES determination. So this is magnitude 1/2, signal to noise ratio 1/2. The surface brightness cut with the error mass becomes 2, the density of artifacts, and the fraction of flux outliers. So they're very comparable, and this is the first time that we can do this for a survey, even before commissioning starts. So this is something, this is a major milestone because it allows us to run as a benchmark for future evolution of the pipeline. So now I'm gonna take the last minutes that I have to show you, after all this, what we can do with light curves in DC2. So we generated simulations using SNIa software, something that has been mentioned multiple times already today. So we create Monte Carlo catalog simulations to reproduce our sample. We know that we can match the photometric properties of our light curves using information from the images that we have in DC2. So the cadence, the depth, the scene size, the error, and the sky noise. And so we generate another set of light curves. These light curves, we can process them in the same way as the data, the DC2 data, fitting them with the SOL2 model. And I'm showing you here the distribution of parameters that we obtained for the simulations and the DC2 data, and they agree very well. So yeah, maybe I should skip this. Is just the efficiency of light curve fitting if we are missing light curves because we cannot fit them correctly, and it's very similar in the simulations and in the data. And finally, we can apply bias corrections to this set of light curves and put them in a Hubble diagram. So this is what we get. In red, we have the simulations, and in black, I'm showing you the DC2 light curves. Of course, we needed a low Z sample, so we had to simulate additionally a low Z sample that gets the same processing treatment. And what we can do with this is check the cosmological parameters. So what we can infer from these light curves and this Hubble diagram is statistically in agreement with the DC2 original cosmological parameters. So we show that this is not unbiased. So basically, the conclusions that we have are multiple. We show results of using an integrated pipeline to analyze the DC2 LSST images. We estimate several performance metrics, and we compare them to precursor surveys, and we find a good agreement among them. We apply standardization techniques for SN1As and fit for cosmological parameters, and we find that the biases in the most relevant ones in W and omega matter are consistent with 0. So an additional thing that we can infer from here is that we are able to reproduce the light curves using these catalog simulations. And I think there are a few useful results to highlight here. So if you want to create, for instance, simulations of SN1A sample for Rubin, now you have the DIA efficiency as a function of signal to noise ratio, which is a key ingredient. You have the median depth of filters, so something that you can corroborate if you are finding similar things. And we have the photometric performance characterized correctly. So one of these things will be, for instance, excess scatter. This is also benchmark for to track the pipeline evolution. We all know that the LSST stack is changing all the time. So these metrics are essential for us to know how the pipeline is changing and track that. And then finally, you can definitely, if you're in DESC, use this data set of light curves to perform whatever analysis you want. There are so many things that maybe are not updated, but you can definitely use it. So the stack is not the current stack. Is not the largest DIA dataset anymore because DB 0.2 just launched, I think 15 or 1 week ago. And then the cadence. So I hope you, I don't know. Yeah, if you have questions, thank you for listening. Yeah.
All right, thank you, Bruno. Any questions? Gotham.
So the other risk with some of these image level simulations is we're always limited to testing whatever cosmology was underlying and inserted into the original pixels. And typically that tends to be just lambda CDM. But of course, DESC's primary mission is to see if it can find any evidence for dark energy that's not just a cosmological constant. How do we go about, do you think, actually starting to do pixel level simulations where we want a non-standard cosmology, something more weird?
This is a good question. I think if yeah, just thinking right now, I would suggest to start with DDF. I think this is the missing part of whatever DC2 analysis is that we are not using the pressures, high cadence, and very deep images that we could have in DC2. So I think I would do that, and if needed, I think I would reproduce whatever we simulations have been done with multiple cosmologies. I do think that if you simulate 300 square degree, it took us a lot of work. So you can infer cosmology from just 30 square degree as DES have done. So probably a smaller subset and just test with that. I think that'll be my 2 cents.